Hello everyone and welcome to lecture. In today's lecture, what I want to do is introduce the cross product and a number of different properties of this cross product. You'll remember in the previous lecture, we defined the dot product which had two really nice ways of computing it. This is for vectors A and B. The dot product could be computed using A1 times B1 plus A2 times B2 plus A3 times B3. It's just the multiplication and the sum of the multiplication of each one of the components of the vector. This is the so-called algebraic form of the dot product. We also saw a really neat way of writing down the dot product, which is called the geometric form of the dot product, which is the length of A times the length of B times cosine of theta. And today what we're going to do is do the exact same thing, but look at what's called the cross product, which is a different type of product that we can have between vectors. So remember, our vectors here have three components. A has A1, A2, A3, and B has B1, B2, B3. So the cross product between vectors, notation-wise, so the cross product notation is just the times symbol, so A times B. And when we're computing this, we always want to kind of draw down a copy of A1, A2, A3, so this first vector, and the vector B1, B2, B3. And there's going to be a very interesting way of computing this, which at first may not make much sense to you, but I'm going to go through and show that the geometric form shows that this method that we're going to have for computing this makes a lot of sense. So the idea is, first off, that the cross product of two vectors A and B is going to give you a new vector, unlike the dot product. The dot product just gives you a scalar. Right? This is always going to be a number. While the cross product between two vectors is going to give you a new vector. So it's going to have three components. Specifically, the way that we compute this is that for the first component, cross off the first row, A1, B1, and then we multiply diagonally A2 by B3 and A3 by B2. And then we subtract these. So it's going to be A2, B3 minus A3, B2. That's how we compute the first component of the cross product. The second component is computed in a very similar way. We cross off the second row, and we consider A1 times B3 minus A3 times B1, but be careful, you have to add in a negative sign in front of that multiplication. A1 times B3 minus A3 times B1. And then lastly, the third component we get by crossing off the third row and doing the multiplication and then subtraction of a1 times b2 minus a2 times b1 with no negative sign. So just a1 times b2 minus a2 times b1. And there you have it. This is how you correctly compute the algebraic form of the cross product. For any two input vectors A and B. You're going to get a new vector when you take the cross product of A with B, and these are going to be the components of that new vector. Now, at first, this probably doesn't make much sense geometrically where this is coming from, but what I want to do is, directly kind of move into why this is working geometrically and what exactly we are getting geometrically out of this. And this is going to lead us to the geometric form of the cross product. So what I've just done is drawn a picture of these two vectors, A and B. This can be in any general direction. And I've also repeated A on the tip of B and repeated B on the tip of A because this shape, called a parallelogram, is going to be very, very important in relation to this cross product right here. I've also denoted the angle between these two vectors in 3D as theta. The first thing that I want you to note is that this parallelogram is lying directly on a plane that's essentially determined by these two vectors A and B. This plane has some normal vector. I'll call the normal vector n hat. And this is perpendicular to the plane formed by these two vectors. So it turns out that the area of this plane is the same thing as the magnitude of this cross product right here. And you might not believe me, so what I want to do is go through and show this. Specifically, if we look at the magnitude of A cross B squared, this is going to be equal to A2B3 minus A3B2 squared plus this squared, the negative one's going to go away, and we'll just get A1B3 minus A3B1 squared plus A1B2 minus A2B1 squared, which admittedly is a very long expression, but we can certainly go through and FOIL each one of these terms out and see what we get in the hopes that it simplifies. So I've just wrote out each one of these terms that we're going to have to FOIL out, and I'm going to go for the world record run in foiling. I'm going to do each one of these at the same time. And there you have it. I've just FOILed each one of these terms out. And this is getting increasingly long. It's getting very, very long here. So it's looking like we might not be able to simplify this. But incredibly, right, this is going to simplify very, very nice if we just do a little bit more algebra and rearranging of terms. And the mathematical trick here is going to be adding and subtracting 0 from this expression in a very nice way. Specifically, if you notice that you have the pair a2 squared, b3 squared, a3 squared, b2 squared, and so on and so forth. But we're missing, so we have all the separate pairs of numbers for a1 for a and b. What we don't have is a1 squared, b1 squared. So I'm going to have to add in to this entire expression an additional 3 terms, a1 b1 squared, a2 b2 squared, and lastly a3 b3 squared. And if I add in those terms, I have to also subtract out those terms as well. So I'm going to end up subtracting out the terms a1 b1 squared plus a2 b2 squared plus a3 b3 squared. And then we also then have, if I factor out a negative sign from each one of these, plus each one of these terms here. Then I'm going to need a little bit more room right here. So take a second and look at this and make sure that it makes sense to you. I haven't changed what's on this line going to this line. I've only added in 3 terms and subtracted 3 terms, which is the same thing as adding 0 to this expression. But what's amazing is we can now recognize this first parenthesis right here is the same thing as the expansion of a1 squared plus a2 squared plus a3 squared times b1 squared plus b2 squared plus b3 squared. This entire parenthesis is the same thing as the multiplication of this times this minus a1 times b1 plus a2 times b2 plus a3 times b3 squared. So if you FOIL this out, you get all of this stuff in this parentheses, and if you FOIL this squared out, you get all of this stuff right here. And take a second to appreciate that, because this is a really incredible step here that we've just done. a1 squared plus a2 squared plus a3 squared is the same thing as the length of a squared. b1 squared plus b2 squared plus b3 squared is the same thing as the length of b squared. And this quantity in the parenthesis is the same thing as the algebraic form of the dot product. So this thing squared is going to be the length of A squared times the length of B squared times cosine squared of theta. I can factor out this squared term and this squared term to get 1 minus cosine squared theta, or the length of A squared times the length of B squared times sine squared of theta. So what I've just shown is that the length of A squared, or A cross B squared, the length squared of the cross product vector, is always going to be equal to the length of A squared, length of B squared times sine squared of theta. Which means that the magnitude of the cross product is always going to be equal to the length of A times the length of B times the square root of sine squared theta. Which, because theta is between pi and 0, normally the square root of sine squared theta is the absolute value of sine theta. For theta in this interval, sine of theta is positive, so the square root of sine squared theta is just sine theta. So this is quite incredible, and this is what the magnitude of the cross product is, and it's giving us a hint at the geometric form of the cross product. Because if you think about what this quantity is, if we draw a straight line from B down to A, the height of this parallelogram is going to be the length of B times sine of theta. The base of the parallelogram is the length of A. And the area of this parallelogram is equal to the height times the base, which is the length of A times the length of B times sine theta. So the magnitude of the cross product vector will always be the area of the parallelogram spanned by A and B. So this is, I think, very, very cool. It's a very, very neat result, and it gives you exactly geometrically at least the magnitude of this cross product. Now, to go a little bit further here, right, we're actually going to see that the cross product vector will always be perpendicular to the vectors A and vectors B. It'll always point perpendicular to these two vectors A and B. So if you have a unit vector that points in this direction, perpendicular to both A and B, we can write the cross product always in its geometric form, which is going to be the magnitude of A times the magnitude of B times sine of theta times the unit normal vector in that direction, where you can always calculate this unit normal vector by taking the cross product and dividing by the magnitude of the cross product. And this is the true geometric form of the cross product. And just like for the dot product, in various situations the geometric form is more useful, and in various situations the algebraic form is more useful. So this is a slightly longer calculation than the dot product calculation, but it's amazing to me that this works out so nicely mathematically. It's always been amazing to me. And so what I want to do is briefly go over some basic properties of both the dot product and the cross product, so that we have them kind of written down and you can always kind of reference in your notes. And these properties are going to include properties that allow us to directly show, right, that the cross product is always going to be perpendicular to the original vectors used in forming it. So I'm going to start with some dot product properties, and I'm not going to really prove these right now because they're relatively easy to go through and prove. I recommend that you do all of these proofs using either the component form or the geometric form of the dot product and the cross product, because that will really help you get a feel for how to do calculations with these vectors. But this first dot product property is that it's commutative. The order in a dot product does not matter. You can do A dot B or B dot A and you will always get the same number. The next property is associativity of scalar multiplication. So you can have, say, alpha times A dot product with B vector is the same thing as A dot product with alpha times B, which is the same thing as alpha times A dot product B. All of these are relatively easy to show using either the algebraic or the geometric form. The next one is distributivity of the dot product. And this is essentially the statement that A dot product with B plus C is the same thing, will always be the same thing as A dot B plus A dot C. The nice thing with this as well is that because of commutativity, so this is, remember, associativity of scalar multiplication. So because of commutativity, A dot B is the same thing as B dot A, and C dot A is the same thing as A dot C. So we can rewrite the order here for each one of these and rewrite this as B plus C dot A. This is something that is not going to be true for the cross product. So oftentimes in mathematics you have different properties for different operations. But these three are the most basic algebraically useful properties that you always see used. We even used the associativity the other day when we were pulling out a constant from the dot product with projections. So this is very, very, very important. The other two we have that we've already kind of seen. The zero vector dot with A will always be 0. And A dotted with itself is always the magnitude of A squared, because A dotted with itself is A1 squared plus A2 squared plus A3 squared. There's a nice connection between the norm and the dot product, so the algebra, And the idea here is that this is one of the reasons why it's very, very nice to choose the 2 norm when you're using a norm. So anyway, these are the dot product simplification rules. We have 3 basic cross product simplification rules. First one is that it is not commutative. So it's not commutative. A cross B will always be negative B cross A. And, we can go through and show all of these, and I recommend you do using both the algebra or algebraic definition of the products as well as the geometric definition. But this simply comes about by when you switch where A and B are in each one of these expressions, you're going to get negative sign that pops out in relation to the original order of A and B. So it's anti-commutative. It does have nice associativity properties similar to the regular dot product, which is that alpha A cross beta B is equal to alpha beta times A cross B, which is pretty much the exact same thing as this associativity law. And the last one for the algebraic properties is that A cross product B plus C will always be A cross B plus A cross C, and vice versa. B plus C cross A will always be B cross A plus C cross A. This is sometimes called left distributivity. And then right distributivity. But it's really important for me to point out that these things in general are not equal, because A cross B is not the same thing as B cross A, and A cross C is not the same thing as C cross A. And so unlike the dot product, distributivity isn't its own property. We have 2 separate types of distributivity that have to be talked about. But these are very, very commonly used simplifications. You also have that the 0 vector across any vector is going to be equal to 0, or the 0 vector. Then we have 2 very interesting rules for the dot product and the cross product, which kind of combine the 2. The first one is called the triple cross product. The triple cross product of 3 vectors, A, B, and C, is going to be the same thing as the dot product of A with C times B minus the dot product of A with B times C. This is a super useful relationship because it kind of brings down a level of computation. Calculating 2 cross products in a row can be very, very difficult compared to just computing, this dot product, this dot product, and then subtracting the 2 vectors. So this would be, out of all of these, one that I would go through and prove for yourself. It would be a very, very good exercise. For you to go through and prove that. The last thing that I want to talk about for the dot product and cross product is, in their properties, is this new thing right here, which is the dot product of some vector C with A cross B. This is a name. It's very important. It's called the triple scalar product. And here I just want to specify, so we have a vector C, a vector A, and a vector B. This is equal to the length of C times the length of this vector, A cross B, times cosine of theta, where theta is the angle between the new vector C and the unit normal vector of the cross product, or the direction of the cross product vector. So whereas A cross B is a new vector that's perpendicular to both A and B, and so C here is a new vector. And this triple scalar product is actually very, very important. What you can actually see is that if I visualize this, so I took the drawing from before and just wrote down A, wrote down B, and then I wrote down this vector C, which is a new third vector. And remember, this plane is just the plane formed by A and B. And if we draw a copy of this plane, 3 copies of the vector C, and on the tip of C I put this plane, and so I make copies of all the vectors. The shape that is formed here is called a parallel pipette. Which you can basically think of as just start with a parallelogram and then drag the parallelogram up along some vector C. This is this 3-dimensional shape that's formed. You think of it as like a 3D parallelogram. But this is what it's called mathematically. And we have something very interesting here. Right? We know from the cross product derivation that the magnitude of A cross B is the area of the parallelogram spanned by A and B and, well, not only that, we know that the height of this parallel pipette, so this is not the distance of C. The distance here of the vector C is the norm of C. That's this distance right here, or the distance of any one of these green vectors. But the distance that I'm after here is this distance right here. This height right here. And if you kind of think about this, remember theta is the angle between the unit normal vector and the vector C. This height right here is going to be exactly the length of C times cosine of this angle. But this angle theta is not the same angle theta as in the previous drawing, but this is the angle theta between the unit normal vector n hat of the cross product of A and B and the vector C. So if you were to consider, say, the volume of this parallel pipette, the volume is going to be, and the volume formula for the parallel pipette is, it's the base area times the height for the distance here, right, of the parallel pipette. Similar to how the area of the parallelogram is the length of one of the bases times the height. But this is incredible because this means that the volume of this parallel pipette is this area of the base, which is the magnitude of A cross B times the height, which is the length of B times cosine of theta. And as well, this should also be and I just realized that I have to be a little bit more careful here. So sorry, the height here has to be the length of C times the absolute value of cosine theta, because cosine theta could potentially be negative depending on what the vectors A, B, and C are, or how the vectors A, B, and C are related. This has to be the absolute value of this right here. And this has to be the absolute value then of this right here. Just to make sure that we're not getting a negative value of the volume. But the point here is the following, right? The point is that this combination of quantities is exactly the volume, right, of this parallel pipette, which is the same thing as the absolute value of the triple scalar product, A dot B cross C, of those three vectors. It's a huge idea, very important formula, and we can see it directly from just applying right here the algebraic or the geometric form of the dot product. This is all we've done right here to get this relationship. And you can also go through and write this as C1 times A2B3 minus A3B2, and then minus C2 times A1B3 minus A3B1 plus C3 times A1B2 minus A2B1, which is the component or algebraic form of this triple scalar product. So this is really neat. And I think one of the last things that I want to show here in terms of a connection is that this is actually very, very relevant in terms of what's called a cofactor expansion of a determinant, specifically in linear algebra. If you have a matrix A, and I'll write the matrix down as C1, C2, C3, A1, A2, A3, B1, B2, B3, similar to how we computed the cross product before. We have that the determinant of this matrix A can be computed by, say, for the first term, crossing off the first row and the first column of this matrix and doing a determinant of this smaller matrix, which is A2B3 minus B2A3. This has to be multiplied by C1. Likewise, we have to subtract the C2 term. We cross off the first row of this, or the second row, or the first row of this, second row, second column of this, which will give us C2, negative C2 times A1B3 minus A2, or B1A3. And then lastly, our last computation, cross off the first row, multiply A1B2 minus B1A2. So for any 2 by 2 matrix, this is how you calculate the determinant of a 3 by 3 matrix. For any 2 by 2 matrix, the determinant of the 2 by 2 matrix, say just in general, for instance, A2, A3, B2, B3, the determinant of this 2 by 2 matrix is computed by multiplying the diagonal components, A2, B3 minus B2, A3. So So this process that I've shown here is called cofactor expansion, and is useful if you're interested in a deep connection to linear algebra and solving linear systems of equations. I won't be getting into that in this lecture, in this course, but the interesting connection here to geometry is that the determinant of a 3x3 matrix is the same thing as the triple scalar product of the columns of that matrix. So this is a super, super useful idea. And you will see, at least in some degree, this idea applied in your multivariable calculus class when you integrate in a new coordinate system in 3D. So when you do a triple integral in a non-Cartesian coordinate system. So this is just, like I said, the cofactor expansion of the determinant of a 3x3 matrix A. You start with the 2x2 matrix. The definition of the determinant for a 2x2 matrix is just the product of the diagonal minus the product of the off diagonal. And this is the cofactor expansion method of calculating the determinant of a matrix A. The interesting thing for us is that this is the same thing as the triple scalar product of these vectors, C, A, and B. So what that means is that the triple scalar product, which is this combination of values algebraically, is the same thing as the determinant of this 3x3 matrix, which is sometimes written as C1, C2, C3, A1, A2, A3, B1, B2, B3, with lines right here to denote the determinant of this 3x3 matrix. But the real interesting thing here is that this is geometrically the signed volume of the parallel pipette spanned by A, B, and C. And that's what we showed right here. I say signed volume because this cosine right here could be negative or positive depending on theta. If you take the absolute value of this, you will always get the positive volume of this parallel pipette. So the last thing that I want to do today is give an introduction to what are called parametric curves in 3D. And believe it or not, this is going to be very similar to parametric curves in 2D. And this topic is going to be the topic that we're going to end the course in with probably 2 more lecture videos. Well, we're going to give a relatively easy introduction here to a parametric curve in 3D. Just like for 2D, parametric curve is a curve, but now it's going to be a curve in 3-dimensional space. So we have not just x and y, but x, y, and z. And what's nice now is that we also have our tool of the position vector from the vector stuff that we've just been doing. So I can always describe a parametric curve by its position vector at a point r, which is a function of some parameter t. Right? Before, when we defined a parametric curve in 2D, we had a parametric curve is a curve with x is a function of t, y is a function g of t for t in some interval from a to b. But to make this a parametric curve in 3D, all we have to do is specify the z coordinate as some new function h of t, and what we get is exactly a parametric curve in 3D, which is described by points x, y, z in three-dimensional space, which is the same thing as f of t, g of t, h of t. So this is really very cool, and I think very important to see how to do, because applications of this abound, right? If you want to, say, figure out the trajectory of a moving mass, or a moving mechanical robot arm, or the trajectory of, say, a particle in a particle accelerator, right? All of these and more are examples of parametric curves. These things define motion of point particles in space. We typically write this as, like I said, r of t, which is simply the position vector that goes out to the point. So this is going to be the position vector f of t, g of t, h of t. And this gives us a nice description of the position vector going out to any point on this parametric curve. This is, say, r of t2 for some other point on the parametric curve. And so, to give you an example, what I'm going to do in this lecture is stick with a very simple type of parametric curve. That's the equation of a line in three-dimensional space. This is probably one of the simplest type of parametric curves. And the idea here is that the only thing we need to define a line in three-dimensional space is a point in three-dimensional space, r naught, that the line passes through, so we'll go out to some point r naught, and we'll pick a direction as well. We need a direction. So you go in this direction. This direction vector doesn't have to be a unit vector. We'll just call this vector v. So it does not have to be a unit vector. The line going through the point r naught is exactly the collection of all points in three-dimensional space that go along the vector v. We know that any multiple of v is going to be a scaled component of v. So we say that r of t, or the parametric equation of the line in 3D space, is going to be the initial starting point of the line r naught plus t times v. And this is for t in some interval. Really, the entire line is t in the infinite interval from negative infinity to positive infinity. So t from negative infinity to positive infinity. Now this is giving you this because if you plug in, say, just t equals 1, what point do you get when t equals 1? You get r of 1 is r naught plus v, which is going to be exactly this point at the end of the vector v. So R naught plus V, we'll color this in pink, gives the position vector of this point right here. R naught plus negative 1/2 times V. For R of negative 1/2 is going to be R naught minus V over 2, which is going to give you this position vector right here. So I think you can clearly see that for any value of t that you've suitably chosen, you can get any point on this line. And all you need to define a line is just a point and a vector that gives the direction the line is going. Now, an important thing is to kind of always see that you can take this equation for the line, and this will be similar to something we can do for a general parametric curve. And we can rewrite it as R naught plus t times the magnitude of the vector v times v divided by the magnitude of v, which is just v hat, or the unit vector in the direction of v. So this is a very neat idea because it essentially says that we can kind of decompose motion along the line into two separate parts: the magnitude of what's called the velocity and the direction of the velocity. This is an important idea that we'll end up seeing as very important. But the idea is that you can see this equation reduces to three separate equations. When you plug in x, y, and z, you get that x is equal to f of t, which is x naught plus v1 times t. Y is equal to g of t, which is y naught plus v2 times t. And z is equal to h of t, which is equal to z naught plus v3 times t. So really this is very, very nice and matches up extremely well with what we've done before for parametric curves in 2D, but this is now a line in three-dimensional space. And this here is a 3D plot of this parametric curve. It's pretty easy to do 3D plotting in Geogebra 3D, similar to how you do it for 2D plots as well. Just the curve command, where you put in the x coordinate of the curve, the y coordinate, and the z coordinate of the curve in terms of how it's parameterized. But this is the helix that I talked about before: a cosine t, a sine of t, t. And you'll see that b really makes a lot of sense as a parameter because it really kind of gives you the rate of growth of this helix. The smaller b is, the closer to 0 b is, the closer this helix is going to be to just the circle. And at b equals 0, you get exactly the circle. B is negative, you get negative helix. And if I increase the range of the parameter value to 10 pi, you can get multiple loops of the helix. I think this is a pretty neat demonstration showing really what a parametric curve is and how, as you trace through the parameter, you get different points on the curve. So in the next couple lectures, what we're going to be doing is really investigating these things and seeing what similarities and differences there are to parametric curves in 3D from parametric curves in 2D. But that will be all for today's lecture. Thank you very much for tuning in. I hope you learned something and you had a fantastic day.